Hi. Uh, so on the last video, we start our discussion about DH representation, and I watched the video that I posted, and honestly, I'm not satisfied with the explanation that I gave to you. So let's just do a briefly review, and again using this illustration of this model, which is uh, this is our three joints connected by these two links. And also this illustration will be our object of study throughout this video, um, when we are while we were doing DH representation studies, and also will be our first example to solve. So let's review this and we can start and continue with our content. Um, we stop right here, on the third step, and I'm about to uh, describe the sequence of four motions that we need to take to do, um, so we can get on our local reference frame. So remember that or the objective of do these motions, uh, the sequence of four motions is to pass to the following reference frame. Okay, so let's review this and we can continue. I wrote a bunch of uh, useful things that we can just pass through quickly just to remember what we were doing. So again, why we use DH representation, and also the additional benefits of use DH representation instead of use the conventional ways, which is the representations using coordinate systems, Cartesian, cylindrical, or spherical. Um, when we use DH, which is the standard way to represent robots, we got the power of do analysis of differential motions. We can do analysis of Jacobian motions. We can do dynamical analysis, analysis of forces, and as robots can be made of a succession of articulations, which is our joints, articulations and links in any order. Using DH representation, we can um, modulate these robots so they can move in different planes. They can have links in NLF. They can be twisted and bended, uh, be at any plane, if we modulate it using DH representation. Okay, what else? Okay, and we got a procedure to use DH representation. So to modulate and analyze any robot configuration using DH, we need to follow these respective steps. So first, we need to assign a reference frame to each joint, and after, we need to use a general procedure to transform from one joint to the next, one frame to the next. And this is exactly what we are trying to do right here. We wanted to transform from one reference frame, local reference frame, to the next local reference frame. And in order to do this, we will apply these four motions, which are standard um, in DH, so we can accomplish this task. Okay, so this is something that now at this point we know very well. Um, okay, this is something nice to review. So if we combine all the transformations from the first joint uh, to the second joint uh, until we got to the last joint, we will have the robot total transformation matrix. And this is valid to the Cartesian coordinate system, the cylindrical, the spherical. Okay. And right here, let's just review this. So we got this joint, this is a joint, another joint, and another joint. So we got three joints, and they are connected by these two links. Okay, and something that I wanted to call your attention is this joint we are naming as joint N. This joint we are assigning as joint N plus 1. So this N plus 1, this N plus 1, N plus 2, this is our index. Uh, and for any number of joints, for example, we can continue, and if we continue, we will have a joint number n plus 3. Uh, okay, and we got um, this axis, and right here is different. It doesn't follow in this pattern. Is not a z index n and followed by z index n plus 1 right here. Again, something that I wanted to call your attention is, and you have to pay attention on this right here, this axis of the joint n is z indexed n minus 1. Right here on the joint n plus 1, we are assigning this joint its axis as zn, and followed by the joint number n plus 2. The axis we are assigning naming as z n plus 1. So on the center joint, the joint number n plus 1, its axis we are naming as dn, and one joint before its axis we are naming as zn minus 1, and taking the center joint as our reference, a joint before it, we got the joint number 2 n plus 2. We are naming its axis as z n plus 1. And right here on the center, this joint on the center, we are assigning its reference frame, which we are calling as local reference frame. We are assigning its axis, as you can see, zn again. Okay, so this axis we are assigning as zn, and we wrote right here that assign a reference frame to each joint. So this is what we are doing. Assign local z-axis and x-axis. So let's see. Another thing to call your attention to point is in DH we don't use representation y-axis. We doesn't use it. All joints are represented by z-axis. Okay, we got this. If the joint is revolute, the z-axis is in the direction of the rotation. Okay, this is our revolute joints because they are cylindrical. They are not. If was a solid like a cube, so this is a not a revolute joint. Will be more like we got this right here, a prismatic joint. So for a cylindrical joint, we got a revolute joint. And if it was a cube, it was a prismatic joint. Okay, what else? If the joint is prismatic, the z-axis is along the direction of the linear movement. Okay. This is the general procedure to transform from one joint to the next. So right here, we got this procedure, these two steps that we need to take. And within these steps, we got a detailed, another procedure, another sequence of steps that we can follow in order to accomplish our goal, which is transform from the local reference frame to the next reference frame using DH. It's not like right here. This is more for Cartesian coordinate system. Again, I'm just repeating something that I already told to you. Okay. So within this second step, we got this procedure. Okay, let's see. There is always one line mutually perpendicular to any skew line, a common normal. A common normal is the shortest. Okay, right here. This is important. We always assign the z-axis of the local reference frame in the direction of the common normal between the previous and the current axis. So as you can see right here, we are assigning the z-axis, this one, in the same direction as the common normal. And the common normal, we know that is this distance between, let's see again, right here, is the shortest distance between the skew line. Right here. This distance, dn plus 1. Okay. So, following the procedure, we assign a reference frame to each joint. This is the reference frame. This is the reference frame. Z and x and y, we don't use it in the age representation. Okay, and we can assign these reference frames using this procedure. Um, okay, we assign on this first step right here z and x. Okay, okay. We also got this uh, angle of rotation theta. So theta n and theta n plus 1 and theta n plus 2. Okay, link n plus 1. What else? We got this angle alpha. Okay, hope this way now is more clear, and we can now take the step 3. And again, the more we pass through this explanation, more we fix, and we can, when we were about to solve the examples, is more, is well explained. Okay, so DH do not use y-axis again, as you can see right here. So we always attribute local frames. Okay, so z points on the same direction as its rotation data. We can notice this right here. Um, is kind of intuitive. Okay. And x points on the same direction as the common normal. Okay, so again, when using DH representation, we follow these steps, we follow this procedure. First, we assign a reference frame to each joint, and this is what we are doing right here. This is the reference frame that we are assigning to this joint. And for the center joint, we are assigning Zn, Xn to a joint. Before the joint on the center, we are assigning the reference frame. Okay, so these are reference frames. And a joint after the joint on the center, we are assigning Z index n plus 1 and X index n plus 1. As you can notice right here, X n plus 1 Z n plus 1 Zn Xn, right here Zn Xn, and again, yeah, we can do this right here. We can point on this direction. This is Xn. And again, the common normal, Xn points on the same direction as the common normal. And the common normal is the shortest distance between the scale line. Okay, Zn minus 1 and X n minus 1, something like that. Okay. And the third step, we need to follow the necessary motions to transform from one reference frame to the next, assuming we are at the local reference frame z xn zn. We do the following sequence of four standard motions to get the next local reference frame. Xn plus 1, zn plus 1. So what we are describing right here is that uh, is this. We are on this local reference frame of this joint on the center, and we wanted to go to the next reference frame. So in order to accomplish this, we need to do these four motions that right now I will write and we will discuss right now. Okay, so let's see the first motion. The first motion is we need to rotate about the z and axis rotate about the z and axis an angle of theta n plus 1. This will make xn parallel to xn plus 1. And again, I'm just reusing the content of the book. We are using the third edition. So this is the words of the book. This is true because an and an plus 1 are both perpendicular to the n and rotating the n an angle of theta n plus 1, we make them parallel and coplanar. Okay, so let's see. First motion is a rotation about the z axis, an angle of theta n plus 1. First is a rotation right here with an angle of theta n plus 1. Let me make this bigger. Yeah. This is n. This will make the n parallel to this will make xn parallel to xn plus 1. So let's check this. Xn parallel to x plus 1. Yeah, it's not perpendicular, it's parallel, as you can see. Yeah. Okay, we can notice this right here. Uh, this blue line, the an plus 1 normal, um, which is x n plus 1 is pointing on the same direction as this blue line, which is our common normal, an plus 1. And we can notice that is parallel right here. They are parallel, okay? Okay, now the step two, uh, the second motion, not step, the second motion. Okay, and if you don't remember, this is a these are perpendicular lines, perpendicular, and these are parallel. Okay, the second motion A is a translation along the z and axis at distance of d n plus 1 to make xn and xn plus 1 collinear since let's see if this is necessarily okay, I think so. Since xn and x n plus 1 were already parallel and normal to the n, moving along the n, we lay them sorry we'll lay them over each other. Let's check this. Okay, right here, a translation of distance dn plus 1 to make xn and xn plus 1 collinear. So let's isolate this right here. And what we are doing, this is x n plus 1, which is pointing on the same direction as this common normal. A n plus 1 is parallel to xn. Xn is this way, so they are parallel. And if we do a translation of d n plus 1, we'll make them collinear. So doing this translation, which means we are moving to this way, so they are collinear. Okay. So let me is this what we are doing? Okay. Now the third motion. Again, another translation. So we need to translate. Um, let me just write this. I forgot collinear. Make them collinear. This will make them collinear. Just okay. You got it. Is this okay? And the third motion, another translation. We translate along the already rotated z-axis along the already rotated, sorry, rotated z-axis, zn axis, a distance of um, a n plus 1 to bring the origins of z-axis, sorry, of xn and xn plus 1 together. At this point, the origins of the two reference frames will be at the same location. So let's verify this. We are doing a translation along the already rotated xn axis a distance of xn plus 1 to bring the origins of xn and xn plus 1 together. Let me see. Let's see this. If we can reuse. Okay, let's check this illustration. Okay, so again, right here is we are doing a translation going to up, and now we are going to the right to get the origins of xn and xn plus 1 together. Okay, we can do this. Now instead of okay, so the origins, they are not together as I'm representing right here. It's something this way, more like this way. Okay, and now it's not this distance. Now let's say they are already collinear. And what we will do is a translation along the z-axis, okay? Along the zn axis, a distance of n plus 1, this distance. And this way, their origins will be at the same location. Origin origin, origin, after a plus 1 translation. Now let me change this color, and they will be um, one above the other. This way. Okay. Bring the origins of xn and xn plus 1 together. At this point, the origins of the two reference frames will be at the same location. Okay, perfect. Now the fourth and last motion that we need to do in order to accomplish our goal, which is transform from one reference frame to the next. Now we will do a rotation. Rotate the ZN axis about the xn plus 1 axis an angle of a n plus 1 to align the ZN axis with the ZN plus 1 axis. At this point, frames n and n plus 1 will be exactly the same, and we have transformed from one to the next. So as you can notice, is a sequence of motions, and it's very intuitive when following this illustration that I made. It's very intuitive that we are doing this transformation from one frame to the next. And if we think these motions, I don't know, like backwards, we can apply this to a frame which is localized before the the local reference frame before this joint on the center. We can not only apply forwards, we can apply backwards. So instead of apply to transform to um, the next reference frame from the local to the next, we can transform from the local to one before, from this joint to the next, or from this joint to one before. And this is one of the reasons that DH is mostly used uh, as a standard. Okay, so let's verify this fourth motion that we are describing right here. So rotate the Z and axis about the X n plus 1 an angle of A n plus 1. Let's see this. So is this axis that we will apply again a rotation, and when it says that about n an plus 1, it means that we are rotating on this direction. It's not saying about uh, let me see, about n. It's not saying about n, which is this common normal. It's saying about an plus 1, so is on this direction. An angle sorry, okay, x n plus 1, sorry, is rotating on this direction, x n plus 1, not x n minus 1, and actually the angle is a alpha, not a. I commit a mistake right here. It's alpha. Right here is an angle of alpha. This angle right here. We are on this local reference frame right here, and we are rotating with this angle alpha. And this way we will align this Zn axis with the Zn plus 1 axis. Okay, so we have described it. We has described it, the four motions that we need to take in order to accomplish a transformation from one frame to the next. And let me continue, still using the words of the book, repeating the exact same four motions between the successive next frames n plus 1 and n plus 2 and so on and so forth for any frames results in the total transformation between the reference frame and the end frame starting with the robots reference frame we can transform to the first joint second joint etc. until the end effector. And something that I wanted to highlight is this sequence of motions or movements remains the same between any two frames. Okay. And of course, just like we were doing all this time, we can generalize to a transformation equation. Okay, so let's generalize to a transformation equation. Um, we can write um, let me see the transformation generalize generalizing Um, so t n plus 1 n. And first, let's uh, learn how to read this. Is a transformation of the frame n plus 1 in relation to the frame n. Okay, and we can call this transformation, we can say that it is the same as uh, a n plus 1. Okay, and we will say that this is the product of the four matrices which represents the four needed motions to accomplish a transformation from one frame to the next. So yeah, from this to this, let me see. Um, we are right here. And we can go to here, go to here, and Zn, no, right here is n plus 1, actually, n plus 1, right here is n, Zn minus 1, x n minus 1, Zn xn, n z n plus 1, x n plus 1. Okay, we got the transformation dn plus 1 and dn plus 1 and okay. Let me highlight this again, since all transformations are relative to the current frame. They are measured and performed relative to the next to the axis of the current local frame. All matrices are post multiplied okay. So let's see. First, the transformation equation. Again, the dodo transformation. Transformation of the frame n plus 1 in relation to the frame n, which is the same as a n plus 1 is a notation that we will use to represent successive transformations, because this is for one sequence of the four motions, and this is represent a sequence with these four motions, and we can have a sequence of transformations. So first, right here, a rotation. First, a rotation about the zn axis with an angle of theta n plus 1. So is a rod Alright. On the z-axis, about theta n plus 1 angle. The second one is a translation along the zn axis, a distance of Tn+1. So trans 0, because it's a translation, and is alongside, let me explain this, as is alongside the z-axis. We don't have y, we have just z, and as is just alongside the zn axis, we just have this component x, right here is x, y, and z, and we just have this component. And another transformation, the third transformation, which is a translation alongside the z and axis, a distance of a n+1. So again, I need to make this smaller. A transformation. Now we have only on the x a x component on the x-axis, and we don't have any other component on the other axis. And a fourth and last transformation, which is a rotation about the z-axis, on the z-axis, about no, is a rotation of the z-axis about the zn with angle of alpha n+1. So rot x alpha n+1. Okay, this is our transformation equation. And again, let's use the same logic that we are using all this time. We will get the characteristical rotation matrices above each respective axis and adapt to to these new uh, matrices. Okay, so let's look for it. Let me find it right here. The characteristical rotation matrices above the axis. Right here. Let me write this. Characteristical rotation matrices. Okay. So the first transformation is this one, a rotation above the z-axis with some theta n+1 angle. So let's use this characteristical rotation matrix and adapt to this new one. A rotation above the z-axis for a rotation above the z-axis, we have this characteristical matrix, and let's just adapt this one right now. Okay. We just need to write right here. Now theta n+1, theta n+1, and right here n+1. Okay, that was easy. And we can't forget to add the scale factor. This is the scale factor. Okay. Now for the translation. We know that for a translation, we always got uh, its main diagonal filled with ones and the rest of the elements are zero. Okay, filling the rest of the elements as zero, and the main diagonal is 1, dn plus 1 is this distance, this translation that we are doing on the z-axis. So x, y, and z. Okay. Now the third transformation, which is another translation, two translations in sequence. Let's do right here. Okay. Again, for translations, we got its main diagonal. The matrix is the elements. The main diagonal, we fill it with ones, and the rest of the elements are zeros. And now is right here on the x-axis. Right here was on the z-axis, and now is on the x-axis, the translation. Very easy, huh? and followed by, and as last, another rotation, the fourth motion. Okay, so is a characteristical rotation above the x-axis. So let's just adapt this characteristical matrix. And now it's alpha, not theta. Cosine of alpha, alpha n plus 1, alpha n plus 1, alpha n plus 1, cosine of alpha n plus 1, and the scale factor. Okay, we made it. We write the matrices. Now we need just to multiply them. So we got the total transformation. Okay, so let me just go up. Let me do it out again. Now this matrix, the translation, followed by another translation. Followed by a last one, the fourth rotation, the fourth motion of rotation, a transformation of rotation. Okay. Okay, and let's do this operation, of course, using the octave. So let me open the octave. I got the command window open. So first I need to load the package. So type pkg load and the package symbolic. Now we need to pass this command sims, and now the arguments that we are using, data, alpha, DNA. Okay, we just need to wait a bit. Okay, now we are ready. We just need to entry with the matrices. So again, right here, let's just adapt this. Let's write data. Data and call this A. Let's copy and paste. The second is the matrix of translation. Right here, let's call matrix B, and right here, let's change for D. Let's copy. And as you can notice, for obvious reasons, we are not using the index n plus 1, just to make easy for us. Now the third matrix is again this translation. So right here 0, and right here is alpha. Okay, I confuse this with this alpha with A, but I think we still are able to get right. Just we don't even to get rid of this A. Let's just leave right here. Okay. Oh, got this bit again when I should call um, SC. Okay, let's clean this. PKG load symbolic data sims first. Sims data alpha in D. Let me see. Yeah, that's it. And no, actually we got A. Yes, we got A. That's right. Yeah, we got A. Okay, let's do it again. First, this one. Now this one. Let me see. 0. And right here, D. And again, for obvious reasons, we are not using the index n+1 to make easier for us. And when we evaluate this total matrix, we just need to write n+1 on the index. Okay, and now right here 0, and right here is, let me see, A. Yeah, A, and we just need to call SC. Okay, just need to copy and paste. Okay, now the last one. Let's adapt this one right here. Let's call D. Right here, 1 0 0 0 0, and right here is alpha, alpha, cosine of alpha, minus sine of alpha, alpha, and cosine of alpha. Let's copy and paste. Now let's multiply these matrices. Okay, and let's take a print. And let me verify this. So we just need to write an+1. Let's first write down this matrix that we obtain a cosine of theta, and writing the index n+1, sine of theta, 0 0, minus sine of theta n+1 times cosine of alpha n+1 cosine of theta n+1 times cosine of alpha n plus 1 and sine of alpha n plus 1 0 sine of alpha sine of theta n plus 1 and sine of alpha n plus 1 minus cosine of theta n plus 1 times sine of alpha n plus 1 and cosine of alpha n plus 1 again. Always remember this n plus 1 is index 0 um, a index n plus 1 times cosine of theta index n plus 1 and a n plus 1 times sine of theta n plus 1 and d index n plus 1 and 1. Okay, is correct. Very nice. And okay, so for now it's all. Can't wait to use this in a real application with a robot arm using the simulator. Actually, let me see if the Roxin it has this future DH representation. Okay, right here on the right side, on the menu on the right side, as you can see right here, DH. Yeah, and we even got quaternions. We got Euler angles. We got this is new for me. Quaternions. Very interesting. Okay, at this moment, I'm not so sure what this DH, what is changing right here on this robot. But we do got DH representation on the simulator. Load the robot, one of the most simple. Yeah, I need to study better this to see how to apply DH representation. But yeah, right here, if we, in other opportunity, I will take a shot at this and apply the steps to be able to accomplish a transformation using DH representation. So we need to, on this, each of these joints, so right here, we have 6 joints. Right here is fixed. 1, 2, 3, 4, 5, 6 with the end effector. 6 joints, and for each joint we assign the z-axis, the zn axis, and the xn axis. So we will get n plus 1 to n plus 5, and for x is the same, xn for x is 2x plus 6, no, x plus 5, x and 2x and plus 5. Okay, for now is all. On the incoming videos, we will start to solve some examples. Okay, so we were able to accomplish this transformation. So we solved this first problem of this illustration. We are transforming from this reference frame to this other. And that's it. Hope you like, hope you enjoy. Thank you for following, and see you in the next video. Bye.